of rho evaluated between A and B. And because it's a minus sign, what I can do is just switch these limits, make this B and make this A. Does everybody understand what I'm doing here? And that means this is going to be equal to rho L over 2 pi epsilon naught times the natural log of A over B. Now that's assuming I put the positive lead at B here. When B goes to infinity, when the radial, B is really a radial distance. When that goes to infinity, then I have rho L over 2 pi epsilon naught times the natural log of A minus rho L over 2 pi epsilon naught times the natural log of B. But as B is tending to infinity, what happens to the natural log? Well, the natural log of 0 is minus infinity, right? John, remember that? The natural log of 0 is minus infinity, but the natural log of infinity is infinity still. Do y'all recall that? So here's the problem. If you're going out to infinity, making this 0 necessarily means the difference between here and any finite point will be infinite. So the problem itself is cast poorly. I'm not really sure what they're after. It looks like what I thought they were trying to get at is just
so
wait, you know what? I'll tell you what this is. They don't say it here. This is a loop, I think. That's the only way you can get something that's finite.
Rho is actually 3.2, not 3. And if you multiply the 3.2 by the 12 nano and the 18 giga, it turns out to the answer 6.4, right? So they're just
you mean
there's an extra 3.2 term in there. So somehow it cancels.
But what he's done here to get 67, to get this number right here, 67.4, what he's doing is ignoring the fact that it's got an infinite difference in potential from infinity to that point. Right? You can't, if you put the 0 at infinity, then you're going to have an infinite increase in potential by the time you get to any point, any finite point. It's just the way it is when you have an infinite line or an infinite plane of charge. If you take infinity as 0 at any finite distance away, if you're measuring from that finite distance to infinity, you will get an infinite potential. What he did here is, I guess you were right, it's just rho L over 2 pi epsilon naught times the natural log of the distance rho, which is...
Well, he's just dividing by rho. He's taking that rho L over 2 pi epsilon naught and dividing by 3.2 to get that. So I don't know how he's doing that, but
that's not the potential. That's the electric.
Yeah, but that's 67.4 volts. That's what you get doing that.
That's wrong. Let me see one thing here. Just last bit of messing around with this. You got 12 times 18. You say it's the log of 3.2?
No, just divide 12 times 18 by 3.2.
Yeah, but
it's
that's the E field. That's that. All right, so that's wrong. The problem is wrong, and that's on me. Okay. The voltage will be infinite. Here's a better question. I'm going to ask you this, since we're on the topic. I want everybody to answer this question, because this would be a typical kind of test question. All right. Well, think about this. This is very similar to what you might see on a test. I'm going to have the X, Y, and Z coordinate system. Right? And now I'm going to have a line of charge that's over 2 and up 1. So at this point, I'm going to have an infinite line of charge in the X direction. Can y'all see that?
Can you scoot it down just a bit?
Yeah.
Thank you.
here we're going to have rho L. It's going to be up. It's going to be over y by 2, up z by 1. But it's infinite in the x direction. Can everybody follow me on that? All right. Now, what I want you to do is tell me the difference. VBA. All right. I want you to tell me what that is. If B is at a point 0, 5, 0, and A is at a point 1, 1, 1. Now, I want you to think about that. This is a very legitimate question, and I can make rho L, for the sake of everybody, I'll make rho L equal to 2 pi times 10 to the minus 9th coulombs per meter. You all follow me? So I want to know what the voltage difference is between these 2 points. So how do you get that? Well, let me try to make this clear to you. First, you kind of need to locate it. 0, 5, 0 is where? It's what? Y equal 5, right? If this is 2, that's 3, 4, 5. So here's 5, and then 0 is right here as well, right? Z equals 0. So this point here would be B. Do you agree with me, everyone? Can you all see it? Guys? I mean, can you see this okay, everyone? That's point B. Now locate point A, 1, 1, 1. Well, I come out 1 on the x-axis, right? Then I go up, over 1, and then I go up 1. So it's right here. This would be point A. That would be point A. Correct, class? It's sort of, 1 over, 1 over, 1 up. And it almost looks like it's on the axis, but it's actually displaced. Correct, class? Now, what you really need is the radial distance difference between these two. So this is over 1, over 2 up 1. So what is this radial distance? Call it rho B equal to. Well, what would it be, anyone? The way you always get distances, it's going to be a square root, first of all, and the difference in the coordinate parameters, and I'll show you what I mean. Now, x doesn't matter. It doesn't matter where it is in x, because it's an infinitely long line charge. X has no bearing. But what's the difference in y? It would be 5 minus 2, right, squared. Agreed, class? What's the difference in z? 0 minus 1, or minus 1 squared. Do you all agree with that? So it's really just 1 squared. And that's going to be what? Square root of, that's 1 plus, and then this is 3 squared is 9. So it's equal to the square root of 10. You agree with me? That's rho B. What is rho A, anyone? Well, I need the perpendicular distance, right? And if you think about it, I'm out 1, I'm up 1, right? I'm out 1, over 1, and up 1. So if you think about it, the only thing that matters is the y and z difference in this point compared to this line. So it's over 1, up 1. It would be like here. Wouldn't that be the perpendicular distance? That would be rho A, class. Do you all see that? Can everybody see that? Okay. Okay. So what is rho A? Just looking. It would be, do it the right way. Square root of what? The difference, actually, here's the rho, goes right to there. Well, what's the difference in the y coordinates? It would be 2 minus 1, or 1 squared. Agreed? All right, what about the z coordinates? Is there any difference? So it's just really 1. Rho A is equal to 1. Now, the voltage difference, VBA here, that's equal to minus the integral of rho L over 2 pi epsilon naught, natural log, and then it would be A over B, right? So here it's going to be rho L over 2 pi epsilon naught. And then it's the natural log of A, where is A? 1 over the natural log of B, which is 5. I'm sorry, the natural log of B, which is square root of 10. You agree with me, class? Show of hands here. How many see what I'm doing? I'm trying to read your faces, having a little time. Can you all see it? All right, now what's that going to be? And I've got a comment here. Well, I'll put it right here. VB A is like VB minus VA. And really, what is that going to be, anyone? I have 2 pi times 10 to the minus 9th over 2 pi epsilon naught. Here, let me write this down. Over 2 pi epsilon naught times the natural log of 1 over the square root of 10. And only thing I'm going to do is that calculation. That's going to be negative. The whole thing here so you can see. Minus 130 volts. Anybody confirm that? You got it? All right. Getting back to the problem. What that means is this. Remember, VBA means you put the positive lead at B, correct? And the negative lead at A. Now, I want you to notice this. The closer I get to this line charge, the greater the potential is, all right? So VB is further away than, VB is, that point is further away from the line charge than VA. And if I'm measuring plus to minus, I've got to get a negative potential. I can see that. You all see that, class? That's something to see. Now, that's a kind of typical problem that I would ask. Fair enough? Another thing, I might have a line charge like this, and then I might have a loop of charge, like a loop in the ZX plane centered at y equals 0. So imagine a loop there. And I might ask for the potential difference between those 2 points. Then you'd have to get it from the line first and then the loop. Do you all see that? Now, the thing about the loop is the only way you can get potential difference easily on a loop is if you're asking for the difference along the z-axis. Do you all remember that? Remember, we only talk about things that are symmetric about potentials or electric fields on the z-axis from a loop, because if you get off the z-axis, it gets very complicated. You get things called elliptical functions that we don't need to deal with. Any questions about this before I go on? All right, let me ask you this. Any other questions about the homework? Getting back to the homework. 348. All right. This is 348. Find the electric field between 2 points. Did y'all try this one, 348? Not a problem? All right. Then I asked you for what? The next problem was, anybody?
351.
Oh, this is a good problem.
Yeah, that one was a little more complicated. If we could go over that, that would be great.
Yeah, I think we need to. So for this one, 351 right here, it says you got two spherical conducting shells with a conductivity sigma, find an expression for the resistance. Now this is a classic kind of problem. And I want to go ahead and do that one. All right. So what it amounts to is you got two spherical surfaces that are concentric. So it's like this. You got a sphere with an inner radius A, and then you got a sphere with an outer radius B. I hope you can see this. Between A and B, assume you've got a material that's homogeneous, and the material has a conductivity sigma. So sigma is between those two. Can you all imagine that, class? Now remember, this is spherical, all right? Now here's the steps you use to get resistance, and I'll go through it slowly. Are you ready? You have to think of this as you would any resistor. It doesn't matter the geometry. And the way you always get resistance is you assume something. So the first thing we're going to assume is I. We're going to assume there's a current I between the two plates. And the current, I'm going to go ahead and try to draw this. Suppose, just for the sake of really a visual aid, I'll have a battery. This is plus and this is negative. And I'll take the plus into the battery and assume there's a little tunnel through this thing, and I'll attach it to the inner point A. So tunnel it through. And then the negative lead will go to the outside, and you can assume the whole outside of this sphere is metal. Give yourself an image of that. You got two metal spherical surfaces, one of radius A, the other of radius B. In between them, you have a conductivity sigma. I mean, a material of constant conductivity sigma. Make sense to everybody? Now, this is some unknown voltage, but what I've done is I've assumed there's a current I flowing like this and then flowing back. So as I gets on this inner surface, it's going to uniformly distribute itself in the radial direction. All right. For any given angle, theta and phi, the current will be the same, the current density. Do you all understand that? Give me a thumbs up if you understand what I'm saying. I'm putting the current into the inner core, and it's going to spread radially to get to the outer surface. Now I've assumed I. The next thing I do is find J. So from I to J, it's always this way. And J is equal to I over the area, right? In a radial direction, AR. So I, this is going to be I, and what is the surface? If I come out a distance R away, do y'all agree if you put a spherical surface at a distance R between A and B, all the current has to flow through it, right? It's a closed surface. Everybody see that? Well, how much current is it? Well, it would be what? I mean, excuse me, what's the area? The area is that of a spherical shell, correct, class? Now you have to know this. What's the area? Can anybody tell me?
4 pi r squared.
That's right. 4 pi r squared, and it's in the AR direction. So that's the current density. The units would be amps per meter squared. Follow me? Our goal, if we assume current, we want to get voltage to get resistance, because voltage over current is resistance. There's J. The next thing we want to get is what? This is the steps. If you assume I, you get J. From J, you get what? Anybody? E, right? You know that J is equal to sigma E, correct, class? That was the last lecture. Y'all remember that? Guys, remember J is the current density is equal to sigma, the conductivity, times E, the electric field. So we can say that the E is equal to J divided by sigma. Here's J. If I divide it by sigma, I get I over 4 pi sigma R squared AR. E field is in volts per meter, right? Everybody? And now I want to get the voltage. Here's something I'm going to give you a tip on. You don't have to worry about the negative sign or anything like that in front of the integral. It's the magnitude of the voltage. It's always the magnitude of the voltage. Forget about sign with resistance. So if we want to get the voltage between A and B, I'm going to reverse them. Technically, it's the integral minus the integral from what? B to A of E. Here's E, which would be I over 4 pi sigma R squared AR, and then dot DL. Now, in spherical coordinates, DL, there's 3 terms, right? But there's just DR AR. Now, do I need these other 2 terms here? The A phi and A theta term, class? Anybody? How about it, John? Do I need to write the A phi or A theta term? Yes or no? Why not? Why don't I? You're right. Just say it for everybody's sake.
Because they end up multiplying to 0.
Well, the dot product of AR dot A phi is 0 and AR dot A theta is 0. So you don't even, I don't even list those. Just put that. Now I know AR dot AR is 1, correct? Now when I do the integral of this, what do I get? I get minus, right? And then there's going to be I over 4 pi sigma is out in front. 1 over R squared integrated is minus 1 over R, makes that plus, right? And then I get 1 over A minus 1 over B. I just put in the boundaries. Do y'all see that, class? How many do? Just do this integration. 1 over R squared dr is minus 1 over R, correct? There's a minus sign out front. You get rid of the minus signs and you evaluate it at A minus B. And you'll notice that A is a radius that I've assumed that's smaller than, oh, sorry. Yell at me if you can't see. Y'all see this right here, class? Now that's the voltage, VAB. If it was negative, if you had 1 over B minus 1 over A, it would end up being negative. You don't worry about it. Just take a magnitude of this voltage. That's the only thing you care about is the difference in voltage between the inner and outer conductor. Understand, class? Now, once you have that, what's the resistance going to be between A and B? Well, resistance is always VAB over the current causing it, isn't it? Are you with me, everyone? I'm going to show you a trick here too. So what is it going to be? Well, it's really just taking this equation, getting rid of I. So it's 1 over 4 pi sigma, right, times 1 over A minus 1 over B. Okay. Now that's the resistance between the inner plate and the outer plate. How many see that? Just show of hands, give me some indication, right? Now I want to show you a trick. Wentworth alludes to this in a discussion, but he doesn't bring it out, so it really sticks with you. And try to appreciate what I'm going to say. So if you have any two-plate system at all, that has properties, that has a permittivity and a conductivity that is homogeneous. For instance, it could be a spherical surfaces. It could be concentric conductors like cores, infinite cylinders with an inner core and an outer core, and between them some dielectric like a coax cable. They could be a parallel plate capacitor where you have just a capacitor I should do it this way. Capacitor plate, and it was actually parallel plate. Right? Doesn't matter. This will always hold true. Now listen. If you take the resistance between the plates and multiply it by the capacitance between the plates, they will always equal resistance times capacitance will be epsilon over sigma. Now, I'm going to show you this with the last example. Just write this down. This is golden. Resistance times capacitance is epsilon over sigma. And I'm going to show you, I'm going to prove it to you. Now, we just calculated the resistance between the spherical surfaces. This is for a sphere. We found the resistance between, I'll just use R here, was equal to what? 1 over 4 pi sigma, right? And then it was 1 over A minus 1 over B, correct? I want the capacitance between A and B. So according to this, the capacitance would be equal to epsilon over sigma, right? Divided by RAB. All right, that would be equal to epsilon, I'm going to put epsilon here, divided by sigma. Now I have to divide by R. So I have to divide by 1 over 4 pi sigma times 1 over A minus 1 over B. Do you all see what I'm doing? You all see that? I've just taken the resistance I found, and first I'm using this equation. I'm going to solve for the capacitance. Well, sorry. I've got this equation right here. I want the capacitance. I just calculated the resistance, didn't I, class? So I take 1 over the resistance times epsilon over sigma. There's epsilon over sigma. There's 1 over the resistance, and that's this. Do you all see it, class? Now, note what happens here. The sigmas cancel, right? And what happens? Well, the 4 pi comes upstairs, right? I get 4 pi epsilon, and it's equal to 1 over A minus 1 over B. Now, we haven't talked about capacitance yet, have we? Class? No, but I'm showing you something. You have an intuitive feel for it because you've had physics. You know capacitance is something between plates too, right? That you calculate. And what I'm doing here is giving you a leg up that if you can find the resistance between two plates, if you have a constant conductivity, if the permittivity is constant, you can find the capacitance just by using this little trick right here. Any type of electrostatic situation where you're talking about nothing changes with time and the conductivity, the permittivity are the same throughout the region between the plates, you can always use this. It's a trick. When professors make up tests, they use this. They will know the resistance is an easy calculation for a certain geometry. So they'll ask the students to find the capacitance, which is probably harder in some respects. You got me on that, class? How many see this? All right. Now what I'm going to do is show you, he talks about dielectrics here and boundary conditions next. I'm going to talk about the dielectrics in general. I can just make this short and sweet so you don't have to worry about it. In the book, let me ask somebody. Ben, when you hear the word dielectric, what do you think of? You're muted, by the way. Okay.
Yeah.
Nothing?
Like a material between two conductors or
well, you think of insulators, right? You think of insulation, rubber, you think of mica, you think of anything that will prevent electricity from getting from one part to another, right? That's a dielectric. Good examples are mica, rubber, styrofoam, anything like that. Now, the thing about a dielectric that's important to understand and appreciate is this. In his book, he shows us dielectrics have something that are bound charge dipoles in them. Like water, you know, is a dipole, but it's not bound in a true sense. Right? Most dielectrics that are solid, matter of fact, all, they have something like this. Press an electric field in a system where there's dielectric. The positive charge is stretched in the direction of the electric field, the negative charge is going to go in the opposite direction. So what happens when you put electric field in here? This electric field puts a force in this direction on the positive and on this on the negative, and it stretches the molecule. That should make sense to you intuitively. Follow me? Can everybody understand that? Now, if it stretches it, that means that energy is being added to the system, because once it stretches, it's not a deformation, it's permanent. You can also get that energy out. When all of a sudden you release the electric field, the positive and negative charge will move back into place. And in doing so, they'll liberate energy in terms of an electric field. Now, I'll have to go through that with you, but can you all appreciate that there's some energy being stored in these devices if the stretch, think of it like two springs attached to the negative and positive center. You stretch them, you leave go of that electric field, they collapse back, right? And in doing so, they'll have energy released back into the structure. This is the idea behind dielectrics. So now, when we talk about the permittivity, a dielectric constant, how many have heard of that term? Dielectric constant or permittivity? Class? You all have, right, in physics. You've heard dielectrics, insulators, you've heard that terminology. What you always have to understand is a dielectric really, when they use that term, is some material's ability to store energy better than a vacuum. So what we do without, and I don't want to spend a lot of time on polarization, vector, he does, but I'm just going to say this. This is the one you remember. When we talk about dielectrics, this is the next section of the book. What we do is we say that the electric field, well, better yet, the D field is equal to epsilon relative epsilon naught times the E field. Here, epsilon relative is the relative permittivity. All right, epsilon naught is called the permittivity of free space, right? Epsilon naught is just about 8.854 times 10 to the minus 12th farads per meter. The relative permittivity tells me how much better the material I'm using is than free space and storing energy. Can you all follow me? Now here's why I say, well, I'll get into this, but it's really about energy being stored. And when we get to capacitors and energy and the energy in the capacitors, I'll make this more clear to you. So that's really been, in a nutshell, dielectrics. You just have to realize that the relative permittivity has to do with how much more energy that material can store for a given electric field in free space, volumetrically. And you don't need to think about it any deeper than that. Free space, when I use that term, it means a vacuum. It means no particles present. However, the air right around us, the dielectric constant of air here is about 1. It's about like free space, okay? That's something you have to kind of keep in your head when you do these discussions. That's dielectrics. He shows dielectrics in the book, and he talks about some things that happen. This is more material science, but the thing you have to really worry about with dielectrics is the relative permittivity. And there's one other thing that in dielectric, and especially with most high voltage insulators, they're rated in a maximum electric field strength. They have E max before you get arc over. You all know how lightning arcs through the atmosphere, and if you put a high enough voltage on a capacitor, you'll short through the dielectric and destroy it, right? Well, E max is usually of the order of, for the atmosphere down here, where we are, it's about 3 megavolts per meter, 3 times 10 to the 6 volts per meter. That's the breakdown strength in the atmosphere. At sea level. When you talk about good insulators, Emax is somewhere between like 10 and 100 times 10 to the 6 volts per meter. Now that's many, many more times than that. And it depends on the material, but the maximum breakdown strength is really the thing in a dielectric you look for more than just about any. And he doesn't say that explicitly, but he does say, I'll show you where I'm looking. You see how right here he says, A more common example of dielectric breakdown is lightning bolt, where sufficient charge has been accumulated to overcome the dielectric strength in air, about 3 megavolts per meter. Everybody's seen lightning, you know what I'm talking about. But it takes about that. Now, in a nutshell, that's what you're worried about with dielectrics. Nothing much interesting. Next thing he talks about, I'm going to talk about this, is boundary conditions. I hope you can see this. You all have your books, class? If you look on page 186, he's talking about boundary conditions. Now, what he's really doing is talking about the perpendicular and tangent, like this is a planar surface, and he's going to be talking about the tangent electric field and the perpendicular, really D field, and what the boundary conditions are. This becomes real important in doing electromagnetics problems. And I'm going to give you my 2 cents worth on this. All right. So when you talk about boundary conditions, first you get a planar boundary. Just put a plane there. Call this region 1 and region 2. Nothing mysterious about that. Now we're going to look, and this is going to, you're going to have to understand, this is going to be at the microscopic scale. If I take a look at an electric field, and assume for now the electric field is only horizontal. So I'm going to have some electric field here. I'll call that E1, and some electric field directly below it, E2. Now, I'm assuming these are both tangent to the surface. They're both parallel, or they're directed horizontally. I don't care about the vertical component. Can you all imagine that, class? Assume that this electric field here is a constant. This electric field is a constant here. Now, here's the argument they make in the book. They're going to say, if I take a little path like this, I'm going to start at point A, and I'm going to integrate in this direction and go back to A. I know what? That the integral of E dot dl, right, is the voltage. Technically, I could say it's minus that from A to B would be the voltage, VBA, right? You with me? I didn't even define the point B yet, but I'm just saying we know that that's true, right? The voltage between point B and point A is really minus the integral of E dot dl from A to B, right? All right. Well, what if I go from here, I go all the way around back to that again? Well, that would be the voltage between VA and A, right? That's VA minus VA, and what is that by definition? 0, right? So if you integrate around this total path, you've got to get 0 volts in electrostatics. Now, that is not true for time-varying magnetic or time-varying electric fields. It doesn't have to be 0. That comes later when we get into propagating electric fields. But if we electrostatics, if we integrate them around, you get 0. Now, remember I said I had an E field here and an E field here on either side of this boundary of region 1 and 2. Well, if you break this integral down, if I take a look at the closed, that simple circle there means it's an integral over a closed path of E dot dl. You can neglect the actual sign, the negative sign. That's really the integral from really A, and let me call it B here. And I'm going to make this height h approach 0. So it's basically a very, very, very thin, or something with very little spatial difference, a thin region where it just goes, I'm in region 2 here and then region 1 here. So if I have the integral from A to B, call that A to B, of E1, or E2, pardon me, E2 tangent dot dl, plus the integral from B to A of E1 tangent dl, I have to get 0. And here's in a nutshell what it is. This integral right here, E dot dl from here to here, it would just be this length. I can make it an arbitrary length L. it would be simply E2 tangent times L. And this integral right here, from here to here, would be plus, well, actually it's minus, because it's going to go from a greater point to a lesser, would be minus E1 tan times L. That equals 0. And here's the upshot of it. I can get rid of the L's and I can take E1 tangent on the other side. So what you're going to see in his book is E tangent in region 1 has to be equal to E tangent in region 2 in order for the voltage around that closed loop to be 0. And in his book, he shows it to you right there. And here's the bottom line. This is formula 3.104. It comes down to this. When you get right close to a surface, the electric field tangent on one side is the same as the other side of any kind of an interference, any kind of a surface like that. There cannot be a discontinuous point. I mean, it can't be like 2 volts and then an instant later go to 5 volts. It's an impossibility. Do y'all see this, class? E tan 1 is E tan 2. How many remember that from physics? Anybody? You had this in physics, I believe, but I might be wrong. Now that's the tangent component. That's always true. The next is, what about the normal component? Well, we always look at the D field. Let me try to, I'll try to do this in the most easy to understand way. So bear with me. So if we take a look at, this is going to represent a plane here. Here's region 1 and here's region 2. And normally what they do is this, they're going to say there's going to be a D field now that we talk about. And he has this in his book. Matter of fact, let me just show you this picture. This will help because Wentworth's book's got a pretty good picture here. This is on page 188 if you've got a book. So if you look here on page, come on, sharpen up. There we go. If you go to page 188, what he does is he says we have a D field in region 1 and a D field in region 2. And he defines a few other things. He's got a normal vector. A normal is just a unit vector that's perpendicular to the surface pointing from region 2 towards region 1. And he's got a tangent vector there that you don't worry about. Now he makes the little pillbox where half the pillbox is in region 2, half in region 1. Can you all see that, class? With me? Everybody can see it. You look in your own book, you can see it. And what he's going to say is, well, I know that the integral of d dot ds over any closed surface, according to Gauss's law, is the charge inside it, isn't it, class? How many remember that? The integral of the d field dot ds over any closed surface is just the charge inside that surface. Do y'all remember that? All right, now look. The integral of d dot ds around the surface is the only thing you have to worry about is this upper surface right here and the lower surface here. The upper surface here and lower surface here. You don't have to worry about this outside surface for 2 reasons. One is, if we take a look at the D field that's in the normal direction, dot the tangent, I mean the normal here would be in the tangent, the dot product is 0. But we do one other thing. We let delta H go to 0. So we're going to make this can shrink down to be almost of no height. Just enough height so it's in the second and the first medium. Now, I know, and I can show it to you right here, the integral of d dot ds that he has here. Matter of fact, this is probably easier. When I got d dot ds right here, can you all see that? This is over the top. That will be equal to d normal 1, a normal, and the differential surface is just ds a normal. And it's really d normal times delta s, whatever the surface is up here. On the bottom one, it's d normal 2, whatever d normal 2 is, he shows here, dot ds, but the unit vector associated with the surface is in the negative direction. Y'all see it has to point away from the closed surface, so it's in the negative direction, class. Everybody see that? Right. Now, what does that mean? When I add these two together, right, I get this, and that has to be the charge inside, right? Well, how much charge is inside? It's really the charge at the surface, right, between those 2 layers, and that charge is going to be simply rho s delta S. And then this is sort of where he's going for. D normal 1, or the normal D field, is equal, or minus D normal 2 is rho S, but generally speaking, the way they write this is D normal 1 is equal to D normal 2 unless there's a charge, a surface charge. Are you with me? Normally it's just D1 is D2 unless there's a surface charge. And if there's a surface charge, this is true, but it's a little hard sometimes to get a handle on, well, which one is, you know, if I'm given an arbitrary region, what do I make region 1, region 2? So Wentworth does this in his book. He'll show you this right here. I hope you can see this. Now do something like star this right here. This is important. If you want me to, I'll rewrite the formula, but it's right here in front of you. And though I despise PowerPoints and everything like this, for this case, it serves the purpose. All right, now the key is A21 is a unit vector normal from medium 2 to medium 1. Now, you all see that? From 2 to 1, A21. Here, A21, the unit vector would point upward. Follow me? This is important. So A21, and then it's a dot product of D1 minus D2 is rho S. The best way to get familiar with this is do a few problems using this and just apply it. And the key thing is getting A21 right. Everybody okay with that? All right. We might as well, I would like to get into boundary value problems, but I don't have time today. And the reason I'm going through this, well, I'll tell you what, I'll stop right here. Instead of doing that, you can look at example 3.24, and I'll tell you frankly, it is not going to be on Wednesday's test. You're not going to get the boundary conditions on Wednesday. You are going to get resistance though, all right? Everybody hear me? Now, because people have concerns over a test, and well, you should, I'm going to give us just my summary. You don't need to write anything down, but you can listen. All the topics we covered so far are going to be on it, except for this last day's topics right here. Both dielectric and boundary conditions won't be. But you're going to need Smith charts. Do you hear me? I want to make sure you print out the Smith charts you like. And I want to make sure you have a compass. I like good compasses like this. If you can see this one, this is a very good one. It's a easy to draw, sharp tip on the pencil. I know people have cheapo compasses, but it makes a difference in some calculations to have really sharp pencils, a good compass, a straight edge, and you know what a straight edge is. I don't need to say this. And when you do the Smith charts, you need to very clearly indicate point 1, 2, 3, 4. And when I ask you what the stub length is, or I ask you what the through length is, you have to first draw a picture of that and then clearly indicate what they are. Now, there's a lot of people that get casual about this on the Smith chart, and they put dots all over the place. I give almost zero partial credit for anything but the right answer, just for your record, all right? So you got to make sure you're exact and clear. The other thing with all this, remember the bounce diagrams? All right, that's a possibility. I'm not saying it's going to be, but that's a possibility. Also, remember when we're talking about a load connected to a transmission line, the power at the load, the voltage at the load, how far away the minimum and maximum voltages are from the load. Do you remember that, class? Those are pertinent questions that I'll ask. And if you'll go through your homework, it's pretty indicative of the kind of stuff I'll be after. Now, when I'm talking about electrostatics, I'm going to be asking for the E field or voltage from the standard charge configurations. And if I give you a charge, like a disk of charge with a charge density that's not a constant, and I ask for the electric field on the z-axis, then you're going to have to come up with that, okay? Or the voltage. So remember, you have to do that. Because it is open book, open notes, I ask you not to get on the computer, but because of the nature of the test, exact answers are very important. You got the formulas. You know, the formulas are right there. I would recommend you do the calculations twice. And to make sure you get the same answer. Literally, I call it redundancy, but I will run the same calculations twice if I have a calculator to make sure I didn't put in something wrong, because oftentimes I do. Now, here, when we looked at this in chapter 3, the big thing was that the coordinates, the spherical and cylindrical coordinate systems had different unit surface vectors, differential lengths, and it caused basically, I think it's much easier to get the voltage first from any charge configuration than to take the gradient of that with a minus sign and get the actual electric field. You all remember doing that, right? Minus the gradient of the voltage is the electric field. To me, it's easier, but you feel free. You're not going to get anything with a, I'm going to assume that you know the electric field from a plane of charge, from a ring of charge, from a sphere of charge, anything like that, the standard canonical geometries. I'm going to assume that you've got that right in your book. We've done all that. So the things you're going to work for are things that you don't have right in front of you. Like if the charge density varies with radial distance. Do you remember how we calculate the D field when the actual charge density varied as either radial distance and spherical or cylindrical? Y'all remember that? Right. Those are the kind of problems that you're going to see. And one other thing I'll tell you. The divergence form of Gauss's law is something you have to be familiar with. I mean, these are fairly simple things. Divergence operators in the back of the book, right? It's just doing the derivatives correct. That's about all I got for you as far as what's on there. Can I answer any questions about the exam, or do you want to do any problems? Consider this an office hour. Anyone? John, you have anything for me? No? Ben, any problems? Carlin? Nothing?
If we're studying like today or tomorrow and we have a problem, can we maybe Zoom call you about that?
Yeah, if you can, especially if you can get like 4 or 5 of you together that have the same questions, that we can all get. You've got that group me, is it? You got going?
Yes.
I mean, if you guys get on there and just network, if you got a common set of, I mean, assemble some questions and then hit me up and we can do it in the afternoon. Now, today, I don't know if you're probably going to be studying today and tomorrow. So tomorrow afternoon, I think I'm pretty free, but I can find out in a second. Let me see how unfree or free I am. Well, this is kind of a miracle. I don't have anything down for tomorrow afternoon, which means that somebody else is going to see that and probably stick some meetings in there for me. Right now, tomorrow afternoon, especially like around 1, if you guys can hit me up with questions. Hey, Tyler, you got my phone number, right?
I think so. Is it on the Canvas page?
I don't know. I gave everybody. Do y'all remember when I gave you my phone number?
Let me make sure.
Here. If it's not here, I'll just give it to you right now. So y'all have it. Please don't give this out. I got enough problems. It's 334-663-2479. Normally, I don't give that out, but can you all see it there, class? And it's in OneNote, so it's going to be there for the duration. It's in homework 12. If you want to call me, Tyler, or anybody, go ahead. But I would prefer I answer all the questions at once. I'm looking at 1 o'clock tomorrow. It's a good time. If you got questions, then ask them then. All right. Anything else for the good of the group? I've been hearing more and more. We had no president's cabinet meeting today, but I understand that there's more and more coronavirus popping up all over, or these breakouts. Did I tell you that one of my students in the other class, he knows 3 of his friends in the Auburn area that tested positive? They apparently went to a birthday party. So I don't know. Does anybody else know people that's tested positive around here? Nobody? How many are in Auburn right now? 1, 2, holy cats. Fowler, are you in Auburn or not? So we got 2, 4, 6, 5, at least 5 people. That's a lot. Are you hearing anything at all about what's going on here from other students? Or they're back on campus today, right? This is the first day of the last 5-week mini-mester, right? Is anybody in? There's nobody in this mini-mester in this class, is there? I don't think so. But I would be the last person in the world to want to go on campus today and teach, just because you're going to have people in your class, you don't know where they've been. All right. Any other questions?